So thanks for inviting me to talk to you guys about the role of glass in the next generation substrate technology. And I want to talk about both opportunities and challenges. So next slide, please. So if we look at the potential advantages of a glass core substrate, glass was first investigated as an interposer back when we did all the research at Georgia Tech about 15 years ago in 2009. And we have, the normal properties like adjustable CTE to improve reliability, higher Young's modulus for better stiffness to minimize warpage, lower electrical loss, lower insertion loss, reduced surface roughness, lower parasitics. Now, at the time that the glass was being investigated at Georgia Tech, it was not for the core of a substrate. It was to be used as the glass substrate. So a little bit different slant on what we're doing today. Next slide, please. So we see a lot of application potential in RF. For example, glass has been proposed as a substrate for high frequency in the terahertz range. So we have companies like Mosaic that's been working with aluminum borosilicate glass and some high purity fused silica with a minimum via diameter of like 15 microns. Some of you might remember about 15 or more years ago when ST used glass with thin film integrated passives on it for an RF transceiver module. This was done internally, and it was internal production lines, but they shifted to laminate because it was less expensive, which keep that in mind. But the glass properties for this were low DKDF properties. Properties look good related to surface roughness, allowing fine geometries, flatness for fine features, potential to do embedded passives. But the competitive technologies for this are fan out with RDL. A lot of companies have demonstrated this. Laminates are less expensive for the lower frequencies, and believe me, people are going to continue to use laminates as long as they can. So what we need is, if we're going to use glass for some of these RF applications, we need some data on how the price is going to compare. So next slide, please. So there's a couple of people that have done some work. There's a 3D Glass Solutions. They're located in Albuquerque, New Mexico. They've done some work on looking at a 79 gigahertz antenna for some advanced driving applications, some RF filters, RF SIP, MEMS, microfluidics. I think what they're known for mainly is some integrated passive work. Next slide, please. You have the work at Mosaic, which is a glass foundry for advanced packaging based in Rochester, New York. They've really focused on doing things with thin glass. They've got a patented solution for high yield thin glass handling. They've got a lot of expertise in cleaning, etching, and via formation. And then they do a TGV fabrication with a laser plus wet etch to allow a lot of different TGV shapes. So they've demonstrated some things, but mostly R&D, not product at this point in time. Next slide, please. So there's a lot of research on glass core today. Absolix, who has a factory in, there's a factory in SK in South Korea. They've done a factory, they've constructed a factory in Georgia, in Covington, Georgia. They got a lot of money from the government, from the CHIPS Act, and they are continuing to develop a process. AT&S has R&D on glass core. Dainippon Printing has a large research activity for 10 years in Japan. They have production plans for a line in Japan. FICT, the Fujitsu company, they have R&D. They've done some prototype demonstrations. Ibiden has R&D. Intel has R&D. Qorvo has R&D with some of the U.S. government SHIP program funding. Simco has R&D. Shinko Electric has a renewed R&D effort. Sony has some R&D. They've introduced that. They have a demo for image sensor packages. Topan, Unimicron have R&D. And then you've got work at glass suppliers like AGC, Corning, Schott. And then the LPKF Vitron division is doing equipment and some glass in via and glass demos. So next slide, please. Sometimes I put a slide up that says your name here, because every time I make a presentation, there's somebody else that says, I got a research program too. But anyway, Absolix is doing a lot of work on the glass core substrate. They have explained that they're planning to offer these high-density glass substrates with embedded capacitors for memory and logic. At one point, they said they were targeting AI. They said they were targeting a 76 by 76 millimeter substrate with 300 micron glass core. They said they've installed a production capacity of 4,000 panels per month, but they have not released any reliability data. Any of the samples that were built at SK in South Korea were done on a round wafer. So the line that's in Georgia is a panel line. So we don't have a lot of data on this quite yet. Next slide, please. Dynapon Printing's been working on this for quite some time. They have a number of different test vehicles. They've 10 years of work in this. They use AGC's glass core material. The glass core is about 300 microns thick with 50 micron vias and 130 micron pitch. They've done a lot of publications of their no change in electrical resistance on their bridge version after 1,000 thermal cycles. And they plan to install a production line by 2027. That size of that panel will be like a 500 by 515. And their target substrate is like a 50 by 50. But, you know, a lot of people would like 100 by 100 depending on what their application is. So next slide, please. So FICT is basically developed a substrate with multiple glass cores that's based on its conductive paste technology. Some of you will remember the Aleve process, where they used basically a resin, a conductive paste between the layers. And so that's what they've applied to this. They say the advantages are low CTE and less warpage for glass, lower stress for the resin layer and less internal stress in the structure, a low transmission loss for small roughness, and they've demonstrated 40 micron pitch assembly. They say that the conductive paste between the cores, each core being about 100 microns thick with 10 microns of this insulating film, 5 microns of copper thickness, that this resin is going to act as a buffer layer. And they say that they can stack multiple cores so that you can fabricate the buildup layers on this core structure. And I think they've done as many as like 3 buildup layers on that. So next slide, please. Intel has been working on glass core work for about at least a decade, with a fully integrated R&D line, about $1 billion in investment, including the manpower in Chandler, Arizona. They have like 600 inventions related to architecture, process equipment, and materials. They did some fabrication of an electrically functional test vehicle with 3 buildup layers, 75 micron TGVs, filled TGVs with a 20-to-1 aspect ratio for like a 1 millimeter core thickness. They're working with equipment and material suppliers to try to build an ecosystem, and they're expected to examine, you know, maybe some thicker cores. And the target is really the high performance things. So like, you know, like AI or high performance servers. So you'll definitely need to do more than 3 buildup layers, but 3 is what's been mostly demonstrated by them so far. Next slide, please. So they've really been pushing hard on the idea of the advantages of a glass core by using it to scale their features. Say you could go to less than 5 micron line in space, maybe less than 100 micron TGV pitch, and bump pitch scaling. They think you could go to less than 25 micron bump pitch on the substrate. And you remember what they mostly are known for is their EMIB technology, where they have an embedded silicon bridge in a laminate substrate. So in the minimum pitch they've done so far on that is about a 45 micron pitch in production. So this would enable them to get to a finer pitch to support the finer pitch of the bump devices. And so there's also, they think they can do more silicon content, larger package sizes. They've talked about stuff up to 240 by 240. And if you look at some of the co-packaged optic requirements, we recently did a survey and people are talking about things up to 150 by 150. So certainly people are looking at how do we get to those larger substrates. They said with high-speed I/O, because they can do smoother copper, ultra-low lost dielectrics and the TGV pitch that would allow them to support that. And then the power delivery, they think that you can use advanced integrated passive, capacitors, things like that in this. But of course you could do that in a laminate material or other materials as well. So, but that is one of their the advantages that they cite. So for improved performance. So next slide, please. So Intel's motivation for this glass, maybe they would get there by 2030 or so in a production type setting, maybe sooner, but that's I think a realistic time frame. The glass core substrate is going to give them this improvement for electrical and mechanical properties. They say it'll have a tunable modulus closer to the CTE of the silicon, dimensional stability so they can do these fine features, going much finer, enable the bump pitch scaling that's needed for the high density, high performance applications, larger packages. Maybe you could do a much larger package size. Now, here's the important question is, and this is what hopefully the high density packaging user group can address, is what happens when you put this very large package on a printed circuit board and reflow that. So we have to get some data. Higher, through-hole density for improved signal and routing. The problem is that the board level reliability for a glass interposer, the work that was done by TSMC about 10 years ago, says that there could be a limit to the number of vias that you can put in without cracking. And the problem is we're going to need about 30,000 vias in a CPU core. So we really need to look at some test vehicles where we're going to have lots and tens of thousands of vias, many buildup layers, and then see what the board level reliability looks like. If we're going to put it in a BGA, that's one issue, or we're going to put it in an LGA and socket that solution. So low loss transmission is quoted as an advantage, and that's one of the reasons that people want to look at this for co-packaged optics, perhaps, and including Intel. So next slide, please. So Qorvo has done a lot of work in looking at this for an RF solution. Basically, they have a glass substrate core that's fabricated in 68 by 189 strips for assembly. So this is for RF applications that are greater than 50 gigahertz. They presented some of their research on a 300 micron glass core that's fabricated on a 510 by 515 panel line with a 12 millimeter exclusion zone in the center and the edge. Assembly was done on strips. Insertion loss really was dominated by the conductor loss. They said they've got package and board level test reliability underway, but they don't have any results that they can report. That glass core substrate had a 222 construction. Maximum would be a 25 by 25 millimeter body size because, for the RF parts, that's more of what you might need. And the copper pillars would be on the silicon die and it'd be attached to that. Now, some of the challenges they've encountered are things like unit singulation of the glass core, delamination of the core metal from the glass, especially at that strip edge, clean microvia formation, maintaining a precise layer-to-layer thickness, and copper density matching on the RF design. And they're still continuing this research with the company that they're working with. Next slide, please. So Unimicron has been working on the research for glass core for a very long time. Their initial research has been done on a 508 by 508 panel, glass thickness of around 300 microns, TGV diameter of around 100 microns, and they've demonstrated a 8.6 millimeter by 6.4 millimeter substrate with 8 micron line and spaces. The key here is to bring up the yields in this process and make sure you can do this without the glass cracking. So again, and do it with multiple buildup layers. Next slide, please. So what are the challenges if we want to do glass? Well, first of all, the infrastructure. There's got to be a supply base for glass core substrates. It's not really well established. You're going to have CapEx for new lines, so people are going to have to commit to that. The OSATs do not have any experience with assembly in glass, so we have to have them have that experience so that we can move this into production. In the area of economics, we have no data comparing the cost performance of this for, this glass core versus a laminate structure with bridges, or a fan-out RDL type interposer structure versus a glass. So we have no idea how this stacks up in terms of, the price comparisons. Via formation. It's very difficult to fabricate the vias in glass without cracking. You have to have some special processes to address the thermal mismatch between the copper via and the glass. So you've got to handle copper via protrusion, copper via sliding, and delamination. And there's been a lot of work and a lot of progress has been made in this area. So you got new methods from Corning, SHOT, all LPKF, laser via fabrications, a lot of work in the via part, but still more work needs to be done. In the singulation, this is where we have the problem of cracks that propagate, and there are a number of methods that are being investigated by people like DISCO on how you might singulate this without having the cracking. And then, of course, we need a lot of metrology for these glass core substrates. Very few people have done anything in that area. And there's no board level reliability data. So next slide. So here's some of the work we need to do. Is we are working currently with a company. We really have to have intelligent processing to detect the chipping of the glass on the edge of the panel. That is very important. We're working with this company called Beltronics, who has an inline metrology system capable of 10 billion measurements of less than 2 micron line in space in less than 5 minutes. That can also check debris in the vias, plus the chipping on the edge with their specially developed algorithm. And we are currently in discussions to bring this technology to a wider market. They build systems. Currently, their systems are used at Intel for the R&D work and the work in their Chandler facility. There's also some defense companies that have used this technology, but we'd like to get this made open to a broader number of companies and have manufacturing in Asia to support some of the substrate activities there. Next slide, please. So one of the questions that we need to look at is, if you do this as a BGA, when you mount the BGA on the board, you have a lot of stresses that are created. During the surface mount reflow process, you've got stresses on both the package and the die. This is an example of an 88 millimeter by 78 millimeter package with a 2 millimeter thick substrates. And as you go through that reflow process, you can see what the profile looks like. So this is going to go through a crying, a smiling, all kind of different positions. So that stress is going to go in places that you don't even know about. And we have absolutely no data of what happens if that core is a glass core, a really stiff glass core. And so that's one of the things that really needs to be considered, is board level reliability data. And we have yet to find anyone who has any data that can be presented. Next slide, please. So in conclusion, where does glass fit? It's used for a lot of applications like MEMS and some RF and things like that. But for the potential to be in high performance applications, we're going to have to do some things in the industry to determine what is the minimum core thickness we can do without cracking. Does a thicker glass core provide the same electrical properties? So maybe 500, 800 might work, or is that going to give us that thickness going to give us the short vias in the core that we desire for performance reasons? What's the maximum number of buildup layers? We've seen 2 or 3 demonstrated, but these high performance applications use 5 or more. We just interviewed people about the co-packaged optics. They think they need 11 buildup layers on each side of a core. We have seen nothing even close to that demonstrated with the glass core. The maximum size of the glass core substrate to pass board level reliability. We've seen a little bit on a 40 by 50 millimeter size and maybe a 50 by 50 millimeter, some of the work that Sony had done, but nothing past that. And that was just specifically to pass, it was an acceptable reliability for their application for an image sensor. But that's not clear that that same reliability test would meet the needs of the high performance applications. So that's yet to be determined. How many vias can you fabricate without cracking? Like I said, 30,000 vias in a CPU core would be maybe typical. And if there's a limit to the number of vias you can put, we need to know that. How do you singulate that glass core without cracking? Maybe we're seeing the possible introduction by companies like Resonac of new core materials that could perform as well as the glass core, but without cracking. And then the question would be, so how do those materials compare cost-wise to what we would have with a glass core? And we don't have any answers of those. And then we need to compare the reliability data of that. So, what we also need to do is look at the total picture. How does the cost of a glass core substrate compare with an option like a silicon interposer or an LD interposer or other kinds of core materials? And we really need some hard data on that. And does the glass core substrate pass the board level reliability test for BGA? Are we limited to a land grid array? And is that acceptable for the applications we're looking at? And perhaps it might be acceptable for our co-packaged optics or some of our server applications, but that definitely remains to be determined. So with that, I think we can flip to the last slide. And I'd like to thank you for listening to the presentation. And I hope you have a very successful meeting, and I look forward to some of the activities. Thank you.